Hello, thank you for watching. My name is Cole James,
I'm Victoria Morato.
I'm Andy Ponce.
and today we're going to be sharing with you our research, Numerical Image Analysis on Galaxies. This work was done under Dr. Jung-Ha An in the Math Department and Dr. Brian Morsany in the Physics Department at Stan State. We've been funded by the Louis Stokes Alliance for Minority Participation, a part of the National Science Foundation, and the STEM Success Program at Stan State. A little bit about ourselves before we get started. Personally, I'm a math major pursuing a physics minor, and I want to get a graduate education. This being said, I wanted to see what interdisciplinary research between these two fields would look like.
I'm also a math major, and I also plan on going to graduate school. But before I started applying, I wanted to get more exposure with research, and I also wanted to improve my programming and coding skills. So I saw this as a perfect opportunity to accomplish both.
I'm also a math major and hoping to pursue a graduate education after graduation. And while this might not be my area of research specifically, I do want to go into interdisciplinary research and have this experience under my belt to better prepare myself.
So, let's talk about some challenges in astronomical imaging. Images in astronomy are used to make important measurements like mass, rotational velocity, etc. However, these images can be incredibly expensive, costing as much as $10 per second on a photo that may take hours to take. Many of these measurements, however, are dependent on an object's distance from the center of the galaxy.
So the purpose of our research is to take that initial step. So we want to be able to find the center of a galaxy, and we want to be able to find the distance between that center and any point in the galaxy. And this is very useful because, like Cole mentioned earlier, we can use this to make approximations on these measurements using lower quality images, which are usually a lot less expensive than having to work with higher quality images.
But before we start divulging further into our research, we want to be able to define two different definitions that were in our research paper. So the first is the center of luminosity, denoted as capital lambda, saying that the brightest point in our image should be the center of the galaxy. Also, likewise, we have that any galaxy that is brightest at its center that has a roughly elliptical shape should be considered an elliptically shaped galaxy, or an ESG. This should not be confused with the actual physical definition of an elliptical galaxy, which is a galaxy that has an elliptical shape but has no internal structure. So once we acquired our three images on MATLAB, we imported them into MATLAB. And what we saw is that two of our three images were actually in a color scale. When we saw that, it had three different matrices. So the first matrix was assigned to the red index, the green index was another matrix, and then we had another matrix, which was the blue. The problem with that is that we want to conglomerate them into one huge database to work off of. So we just did a simple color into grayscale. And once we were able to do that, we finally saw that we had one matrix to work with, and we generated a simple histogram plot off of that. So with our simple histogram plots, we saw a lot of information. First and foremost, we have a lot of these colors on here, and that's actually a distinct pixel in respect to its position in the picture, as well as its intensity level. So the x-axis, or the horizontal axis, is telling us the position in where that pixel is in our image. Meanwhile, the vertical, or denoted as I-axis, is telling us the intensity level varying from 0 all the way to 255, which is its maximum. So what we're seeing here is we have a very crisp peak. This peak is telling us that, again, it's at its maximum of 255, and its position is in the middle of our image.
So, here's a different visual representation of that phenomenon. We developed these contour maps to get more concrete evidence that the centers of the galaxy were the brightest in both directions, not just the x direction. We'll zoom in on IC 1101. You would read this contour map similarly to how you would read a topographical map or a hiking map. This purple ring represents pixels of intensity 50, and everything outside of it has an intensity of less than 50. Moving inward, this blue ring represents an intensity level of 100. So if you are outside of the blue ring and inside of the purple ring, your intensity is between 100 and 50. This process continues into the centermost yellow ring, which represents an intensity value of 250 or greater. on a 255-point scale. So this visually confirms that the center of our galaxies are the brightest.
So if we want to find the distance between the center of a galaxy and any point in the galaxy, we need to know where the center actually is. So to accomplish this, we asked MATLAB to take all of the points in the image that have an intensity of 255 and to throw those points in the matrix. Now the issue with this is that a lot of our images actually have noise in them. And what this means is that we have areas in the image that are very bright and also have pixels with intensity 255, but are not in the center of the image. So if you look at IC 1101, you can see these very bright circles at the edges of the image. These are going to produce pixels that have intensity values of 255, but are not in the center. And this is usually caused if you have stars or galaxies in the foreground or background of your image. So to get around this, we asked MATLAB to trim the edges of our matrix so that we focus more on the center points. And once we have this new trimmed matrix, we take the median of it to find the center, which we denoted as these red ordered pairs. So with IC 2006, the center is roughly at about 1947 in the X direction and 1363 in the Y direction. For NGC 3610, the center is at 645, 632. And for IC 1101, the center is roughly at about 247.5, 288. So now that we have the center of our galaxies, to find the distance between that center and any point of the galaxy, we use the distance formula. And what this does is it takes your X and Y coordinates for each point, you plug them in and you get the distance. So in this example with IC 2006, once again, we take the coordinates of the center, which are 1947 and 1363, and we take the coordinates of the pixel in question, which is 1500 and 780. And when you plug these in, you get a distance at about roughly 735 pixels from the center.
Now that's important information to have. However, pixels is not a very relatable measurement. What we would rather have is something like parsecs that's a little bit more meaningful. So we developed a scaling factor to be able to do that. And this used a couple of known data points, being our object's radii from Earth and the resolution of the images that we obtained in arcseconds per pixel. And I'll take a moment to explain what those two things mean. An object's radius from Earth is the radius of the circle across the night sky that object lies on with the Earth at the center. So that's depicted by capital R in this picture here. From there, we had to obtain our resolution for our images. So this resolution in arcseconds per pixel corresponds to the angular distance across the sky each pixel corresponds to. So to complete our scaling factor, we swept out an angle of 1 arcsecond and used trigonometry to evaluate the length around the circle that encompassed. From there, we had a scaling factor in terms of parsecs per arcsecond and another one in terms of arcseconds per pixel. So we now have a way to relate parsecs directly to pixels. So applying that scaling factor to the same distance computation you saw before, we arrived at 735 pixels across IC 2006 corresponds to approximately 9,135 parsecs in real space.
So now that we've figured out how to find the distance between the center of a galaxy and any point in the galaxy, we constructed a loop in MATLAB that would do this process for every single pixel in the image. And this created a distance matrix, which we then asked MATLAB to display, and it displayed it as these contours. So the way that you read these contours is starting with the innermost contour. This contour lies on all of the points in the image that are roughly about 50 pixels away from the center. The second innermost contour lies on all of the points that are roughly about 100 pixels away from the center, and so on.
So in the future, we would like to be able to apply this contour process to a low quality image and then approximate the amount of light contained within each of those contours using the processes that you've seen in this presentation. From this data, we can approximate these otherwise expensive measurements.
Now, lastly, we'd like to thank a couple people. First and foremost, we'd like to thank both of our advisors, Dr. Jung-Ha Ahn and Dr. Brian Morsney, for helping us with our research in the last year or so, as well as all of their support and mentorship. Next, we'd like to thank the CSUS program on our campus for allowing us to present at our school-wide and now statewide competitions, as well as our STEM Success, RISE, and LSAMP programs for all of their funding and support. Lastly, we'd like to thank our College of Science at California State University, again, for all of their support and guidance. Thank you, and go Warriors.
Go
Go
Warriors.
Warriors.